Our next speaker is Mr. Bloem, and we're talking about how to use your strength.
All right. Set up. Yes, so let me just do one thing.
Yeah, there you
Right. I came up with this title as I was walking here, but this is the most important part. This is very much work in progress. I sort of said yes to, or I submitted my idea for a talk about 6 months ago. Well, 6 months. I'll do the work. The preprint will be out by the summer. It'll be great. But life had sort of other plans. So most of this is work I've done in the last 2 weeks in a sort of mad rush. I think it's still interesting, or there's interesting stuff there, but so please bear that in mind. This is our domain. This is where we are, what we're going to talk about, and we've seen this sort of problem crop up a couple of times already. Basically, the bottom axis here is complexity, Kolmogorov complexity, or many other kinds of complexity, where basically here you see sort of high complexity data, which is completely random, as we all know, low complexity data like a checkerboard pattern. And it's very easy to get medium complexity data. You can just sort of slightly you start here and you slightly up the proportion or change the proportion of black to white pixels, right? And then you have some predictability, and your complexity is going to go down possibly all the way to 0. So just saying, well, medium complexity doesn't necessarily mean that you have interesting data. You can have very boring data that's medium complexity. And then the problem is that all the interesting data that we are practically interested in also lives in this area, right? It definitely doesn't live here because it's not very compressible. It definitely doesn't live here because it's compressible. But if you go to Netflix and watch a movie, it's going to be compressible. It's going to have patterns and structures and ideas and storylines and stuff like that. So somehow it lives here with this kind of boring data. So Kolmogorov complexity basically doesn't tell us whether data is interesting. The long-running question is, can we put something on this axis? Is there some formal way of telling whether a given string is in some universal objective sense interesting? Why do we care? Lots of reasons. It's an interesting question, but it's recently becoming a little bit more relevant because there's a big line of work saying, hey, look, we can actually train good models, universal models, or models that appear to be in some sense universal on synthetic data. So here's a paper that Kevin presented earlier, and here's another paper that doesn't take this sort of universal induction view, but I think that's what they're doing. But in general, so you can have some fairly simple synthetic data generator, you train a big model on it, and it performs really well. And it would be nice if that synthetic data generator could be sharpened up a little, right? So that you actually know you're generating interesting data. There's one area where really, in a practical sense, it would be nice, and also for natural data, that's actually synthetic data, it would be nice if we could take our training data and filter it on the interesting bits, see if we can train something useful more quickly. That's one sort of practical way of motivating this research question. There's sort of 2 lines in the research for how to define this interestingness. One is to take a 2-part code. So you encode your model and then the data given the model. And then you look at how much of that 2-part code is your model. You say, well, the bigger the model is, the more interesting it is. The reasoning is that if you have this interesting data that contains plot lines and patterns, trees and dinosaurs and stuff like that, then your model needs to encode all that, so your model is going to get bigger. So within your 2-part code, it's going to grow. And then there's a long line of suggestions. Basically, lots of people suggesting the same thing over and over again, often pretending that they're the first one to suggest it. Lots of different. That's why we have lots of different names for the same thing. And I just want to. So we're not going to go here, but I do just want to point to this one because it has come up. We've identified some serious problems with this field, at least with the sort of claims that these are universal codes or invariant to your universal Turing machine. But there's this other line of research basically saying well, let me read it out, the thing's blocking it. How much time do I need to compress all of it? And there's fewer ideas here that I know of, because the two main ones are logical depth and computational depth. And basically they say, well, look at your optimal compressing algorithm, add a little slack parameter, and then within that slack parameter, how much time do I actually need to decompress my optimal representation? And again, if you have dinosaurs with great plot lines, then you're going to need some time to unpack all of that. Whereas if you just have a checkerboard, it's a very simple program that can run for very low time. So the question for today is, can we take that logical depth and make it a practical measure of interestingness? Because basically when people were talking about this, we didn't really have practical ways of doing it, right? This was just theoretical. You talk about Turing machines with polynomial time bounds, super polynomial time bounds. Think about it. You couldn't actually do it because when you look at machine learning algorithms that actually compress or learn something, none of them were hierarchical. None of them had depth, where you could say, okay, I'm going to take a support vector machine, and then I'm going to take a deeper support vector machine, and an even deeper support vector machine. It doesn't really work. Support vector machines don't really work that way. But now we have neural networks, right? And you can make a neural network with 1 layer or 2 layers or 3 layers or 4 layers. So the technology has slightly caught up with this idea, and I think it's time to start seeing if we can do this practically. And this is sort of hands-free, so the theory is not developed and turns out to be slightly difficult. So I'm just doing this entirely bottom-up, no theory, just trying it out as best as I can. We'll call it model-bounded depth for now. So we'll let go of the idea of time bounds or computational resources, and we'll just say we have a telescoping model class. We changed the notation at the last second. This should be C, where basically you have model classes with different levels, and each level of the model class contains the previous level. So this could be an increasing time bound, polynomial, super polynomial, etc., like a polynomial hierarchy, but it could also be neural networks, right, with different depths. Then also a 2-layer neural network can do all the things that a 1-layer. So you have again this hierarchical, and then that's what we call our depth, is sort of how deep into this hierarchy. And then BTMs with increasing time bounds are just a special case of this, which increase to the universal Turing machine. And so that recovers this logical depth. And then we'll look at some practical ways of instantiating that idea. So then given something like that, how do we define depth? This is how Bennett does it. He basically says, this is our depth, so these are the levels of our model class. This is the amount of compression we achieve by the best model at that level of our model hierarchy. And then you can see different patterns of behavior emerge. So for X here, we see that we compress pretty much optimally at the bottom levels of our model class, and then adding more levels doesn't really do much except a little dip at the end. And so this gray box here is our slack parameter, where we say, well, if any improvements that are within this size of the gray box, we don't really care about. So this is the cheapest model in terms of depth that compresses our data optimally to the extent we care about it. So that's our depth for blue. And then for red, this last model compresses it by a huge amount. So if we have this much resources available, then we can suddenly compress really well. So this is the depth of red. And the same goes for green, right? So there's a couple of problems with this, especially if we want to do this practically. We only have D levels of depth. So it's kind of coarse-grained in terms of what we can express, especially if we don't have a very deep hierarchy. It's very sensitive to this slack parameter. So if we very slightly change the slack parameter by a constant amount, suddenly we could end up caring about this amount of compression improvement over here, and the depth of the blue line can switch all the way from the lowest depth to the highest depth. So a constant change in your slack parameter can suddenly massively change your depth. And it doesn't really distinguish between Y and Z, right? So both of them can only be optimally compressed at the top depth. but white sort of gradually goes there and doesn't really get much extra benefit from these higher levels of depth. Whereas for Z, it's sort of what we call absolutely non-stochastic. So you really need to go all the way to this higher level of depth to see that that Z is actually compressible, right? To sort of move along, increase your time bounds, that keeps looking random and random and random, and suddenly looks massively non-random. So, but for my money, Z should be considered deeper than that Y. So this is my proposal. Mostly fairly ad hoc, but I think this solves some of the problems. To slightly smooth out the depth. So what we do is we normalize the compression. So we look at this curve, the minimum point, the maximum point, and we normalize that to 0, 1. So 0, 1 is just the optimal compression we can achieve within our depth, and 1 is the worst compression we can achieve within our model class. So all curves start at 1 and all curves end at 0. And then we look at the contributions that every step of this depth makes from D to D plus 1. And that contribution, the amount that the curve drops at that step, we call that the weight W, WD, weight for that depth. Should probably be WD plus 1, so it's the depth that you go to. That's the way you get, because that's how much you gain by going to that depth. And then with these weights, which sum to 1, you take a weighted average over the depths. So if this goes from 1 to 12, you take a weighted average over the integers from 1 to 12, and you get roughly the same thing. So this still gets a higher depth, and most of the depth will be over here because most of the drop happens in this last step for Z. Whereas for Y, you get a roughly depth around here. It's sort of roughly medium depth because every step adds roughly the same amount of compression improvement to your curve, and the X is still over here. And there's no longer a slack parameter. So hopefully this should be a little bit more robust to small changes here and there.
Can you just do the area?
Yeah.
Intuitively, it looks like one, like the blue one has got a small area, the red one has got a big area.
Yes, you can. I did think about that. Why didn't I go with that? I don't know. There was a reason why I didn't do that and did this instead, but I have to sort of try and remember it.
Again, are you potentially for random noise and see, for example, that?
So Z, if you look over here, sort of up to this level of depth, it looks mostly random.
Right. So
because it's incompressible.
So the definition of that in your case is the last point that was shared. No.
No, so that's Bennett's definitions of depth is sort of the level of depth you need to go to in your hierarchy to achieve the optimal compression. And my definition of depth is a kind of averaged version of all the depths, averaged by how much they contribute to the optimal compression. So as you go down here, going from depth 0 to 1 contributes a tiny amount to your compression that you're going to achieve by the end. And again, all tiny amounts. And then here, the last step contributes a huge amount to how much you press. So this is a weighted average where this last step takes most of the weight. So if this is 12 depths, then your depth will be about 12. A couple of details. I said there's no slack parameters. I'm going to contradict myself right away. In some cases, you need a minimum range of compression difference. Because if you look at an uncompressible string and you compress it with this kind of telescoping hierarchies, you get a little bit of noise. Just by some random luck, one model is going to compress it a tiny bit better than another model. So you need a slack parameter that is bigger than that amount of sort of fluctuations to tune out that fluctuations. So if it's there's a minimum range of compression, and if all of the differences are within that range, then we just call it depth 0. And in some of these model classes, I don't need this, and in others I do. And then we monotonize, I think I invented this word, but we make monotonic the series of compression values. So if we see a curve like this, we just take the cumulative minimum so that we get a monotonic curve. You could very easily do this in code. So you can just tell your code, just if you hit this point, your code can just say, oh, I prefer the lower model. But it's actually quite informative to plot it like this, because you sort of see that your model class is not in itself, right? As a neural network, you would like the curve to look like this, and if you see this, it sort of tells you that your neural network is not fitting the data very well. So it's actually quite nice to not do this in the code, but to do it in the plotting. All right, so then we're gonna try 3 model classes from simple to more complicated. Rank decomposition, which is a non-neural network one that we could actually have done when Bennett first proposed his theory. Pixel CNNs, so that's first neural network, and then a pre-trained LLM that we trained on text. And the results, as I say, is work in progress. So these results are relatively promising, and then the Pixel CNN really doesn't work that well. So there's work to be done there. This is our data. So it's all fairly qualitative. I'm just sort of applying this to some pictures. It's largely a very expensive method. So this is also sort of the best we can do for the time being. And basically what you see on the first row is synthetic data to sort of look at our, test our intuitions, and then some random open license images I found on Wikimedia. And the key things to pay attention to, and really the only thing we're trying to achieve at this moment, is to pass our sanity checks, which is that random data, I think Gaussian random data and uniform random data should have low depth. And then these synthetic data, which have a simple program, ideally should also have low depth. And then the rest should have some non-low level of depth, where we just say it's subjective. What the model chooses to do is subjective to our models, right? So we're not aiming yet for any kind of notion of universality. We just say the model class views the data in a certain way, and that we can see how it orders these images by depth. Right, so rank decomposition, if you don't know, basically takes your image as a matrix, so it needs to be grayscaled, and tries to decompose it as the product of 2 other matrices, A and B. And then if it does that well, you just need to store A and B and the residual of those 2. So here's a little picture of what you get as a reconstruction from a low rank image. Just to sort of give you some intuition of how the low rank decomposition, the rank decomposition sort of views an image. And this is, you have a nice closed form solution if you do this, if you minimize it by the distance, by the Euclidean distance between the picture you reconstruct in the original picture. Don't have a nice low rank, you don't have a nice closed form solution if you do it, if you try and minimize the code length. So we need to do a lot more fiddling, and it becomes non-convex and it's harder to solve. But basically you can still find a good low rank decomposition that solves your problem. And note that what you can do is zero out the higher rank. So if you have a rank decomposition at a certain rank, that's your depth, by the way. So the size of this matrix here, that's your depth. If it turns out that actually a lower level in your hierarchy would have been just as good, then you can just zero out these ranks, and they become very easy to compress if you have a good compressor to store your model. And so it's relatively cheap to sort of, if you're at a higher level of your hierarchy, to go back to a lower level. That gives you your rough quantities of the compression. And so here, first result on our data, these are the raw compression distances with rank 0 to 32. So before the normalization. And if we normalize, we see this. It's a bit of a complicated, messy image. Takes a while to see what's happening here. But basically, we have these dotted lines are the non-monotonic ones. So what we see for these random images and these very simple images basically they don't beat the baseline. So at level 0, we just compress the image using KT estimator. And if it doesn't beat that, we sort of think of it as, whatever depth you compress the image at, it uses more bits than that. So you get this highly non-monotonic curve for all these simple images and the noise images. And you get these nice sloping monotonic curves for all the natural images, like this picture of mountains and clouds here. These look noisy, but that's just an artifact. This is actually a satellite image of fields, and this is a sort of texture image of a kind of wallpaper, I think. So that, these, as the model sees them, it fits this sort of sloping monotonic curve very well. And so if you then compute this smooth depth and arrange the images by depth, we see this ordering occur. And we see over here that we are passing with 2 sanity checks. So these images are seen as simple and the random images are seen as simple. These are seen as simple, and then the rest are all the natural images. So really what we wanted to get from this so far. And yeah, apparently this model class thinks the Mona Lisa is boring and wallpaper is extremely interesting. So it's not quite the human fuels of natural data, but it passes the sanity checks. That's a lot.
And also, sorry, this the one at the bottom is the fractal.
Yeah.
Is that the right case? I'm not really thought that would be the generate. So is it
Wait.
the depth would be?
Yeah, if these were Turing machines, this would have low depth, but this is a much shallower model. So yeah, you really have to sort of look at this picture to see what the model has to say. Anything that decomposes really well in this sort of structure should get low depth. But then even this one gets high depth, so even that's not necessarily that predictable. I need to hurry up a little bit. So I tried this with the Pixel CNN. This is mostly negative results. So Pixel CNN does autoregressive modeling of images in row scan order of pixels. Lots of training details. I used frequential coding. If you know, you know. For now, I'll just skip it. And lots of fiddling needed to pass at least one sanity check, but I think I'll just skip to the result. You see here we're in color now because the Pixel CNN sees color. And what we see is that it works for the one sanity check, the noise gets sorted out. So it doesn't compress the noise, which is not that hard to achieve, but it's at least heartening that that worked. But what we see is that the simple images end up really high in the hierarchy. So this I consider a failure. And to give you this sort of the short story, you can look at this one, which is a constant color image. What we're seeing is that frequential coding measures, when you do frequential coding with neural networks, it measures compression and speed of convergence. And as you go deeper in your model class, the SGD converges slightly quicker. And that gives you a better code length because the earlier pixels, as you do this row scan, get compressed more efficiently. And you can get rid of this mostly by, well, a lot of it by early stopping and training until your validation loss reaches certain value, but you can't get rid of it exactly. So that's why you see that there is a benefit as you go deeper and deeper and deeper in your model class to make the network bigger and bigger and bigger, which makes the model think that this picture is interesting.
So you're training the model.
Yeah. So this is purely a model trained to compress one image, basically. I tried it with a prior as well, but that worked, of course.
Basically the depth, the computation depth is like the number of layers, or also steps of gradient descent, or what?
It's a combination of layers and width. So as we go deeper, we give it more hidden channels and more layers. And that also increases the receptive field, right? So as you encode 1 pixel, you see more of the image signal. Encoding 4. but the steps of gradient descent are given based on your validations within the same image. So the model sort of keeps going for as long as it needs to roughly compress the image it's seen so far.
So that is total time, or total computer, or just another?
Layers indeed.
Do you have the, well, when you account for the compute time? Because that will account both for the number of layers, bandwidth, versus speed, and reach total.
No, I don't have that, but it's monotonic in the model size. So the model is bigger in all dimensions. So if you make it, if you go deeper, level deeper in my hierarchy, it will be more expensive by some function that I know. Right. So here's the point I was just trying to make. This is, here you see the differences between depths for this image one. This one's image. And you just see you get a little bit of benefit from faster convergence. So then to the natural language model. So we're switching to text. And now we have a prior. Now we are pre-training, or somebody else is pre-training on web data, the pile to be specific. And Eliuther gave us these 7 lovely uniform models with these sizes. We can treat that as our depth hierarchy, take a chunk of text and see how well does it compress each level of the hierarchy. So it's just one forward pass through your LLM. So long as you're not looking at chunks that are bigger than the context length. That's all you need. And then we have 2 data sets, one of 500 kilobytes, which I just sort of pulled some random data in. All data is collected from after 2021, which is when the pile was scraped. So all data is new relative to the model. And then there's mixed, which is a sort of mixture of 100 megabytes of code used general web data published after. So here are the curves. They look relatively nice and monotonic with some exceptions. And these are my my additions. So I added some random data, pattern data. And we see that in that setting, we see that we roughly pass the sanity check. So if we look at the small data, we have simple data over here. So it's just a sequence of zeros and a sequence going 1, 0, 1, 0, and 0, 1, like a checkerboard, one-dimensional checkerboard. And then here we have random data, which is just, I think I took 16 characters and I just make a random sequence. This is a bit messy, so there's some stuff that looks more interesting to me that the model considers more interesting than the random data, but roughly all of it ends up with the bottom quarter of the data, so it still seems to do pretty well. And then the deepest data looks like this. There's not much to be said about this, except that the code and the LaTeX parts of the data don't really show up. And what we see is short stories, movie scripts, and parts of one of my papers that apparently is according to Pythia. I don't know whether we can draw any strong conclusions from this. And then if we go to the larger data, what we see is that at the bottom, so the least deep, we see all code. This might just be that Pythia is not that good at code because it's been specifically trained on the pile, which I don't think contains a lot of code. But it's interesting that we do see code on both sides. So we see code at the bottom, which is sort of boring code like this. And then more interesting things like this. This is the deepest chunk. So code sort of tends to appear throughout. And here's a strange internet post that quotes the Bible, which is the second deepest chunk. Again, make of that what you will. I don't think it's time for a religious epiphany yet, but who knows, maybe that's. And then finally, a training experiment just to show sort of where I would like to go with this. We select some of the deepest data. The idea is that we select some of the deepest data, we train on it, and then we do better on this subset of the data. So to test that, we select the deepest data, the least deep data, 10%, and one data, which is 10% random chunks, the typo here. And what we see is not exactly the picture we'd like to see, but still something hopeful. So this is depth 6 and depth 12. So now we're training from scratch a neural network on this data. And we see that if you train on the bottom 10% of data, you do really terribly. And if you train on the top 10%, you do well, but not as well as training on a random 10% of data. So my hope is that if you mix random and top, somewhere in between here, you get the optimal result. So the model doesn't do that well if you just give this super good data, but it needs some mixture of deep data and shallow data to get started. And possibly you need some kind of curriculum learning where you go to the top and then you mix in more of this top data. Sorry, yeah, I'm way over time, so I'll end it there. These are my conclusions. But,